Here's video number 2 for the exam number 5 for Math 107. In this case, you're supposed to perform a Gauss-Jordan elimination, but there are no hints. However, the matrix is very simple. Follow directions here. Here are your equations, 2 equations and 2 unknowns, which you know you could just solve by yourself easily, but a 3 by 3 takes too much time on a test. The purpose here isn't to solve the matrix, solve the system of equations. Instead, it is to demonstrate that you know the Gauss-Jordan technique. Okay, so first thing you do is write as a matrix equation. What does an equation have? It's got an equal sign. So I put the coefficients 2, 1, 3, 2 in the first matrix. Next comes the vector of unknowns with the x and y equals solution vector 1 and minus 2. Now write the augmented matrix. For the augmented matrix, you take the coefficient matrix and the solution vector and you put them together. Now you have to do the row operations that will give you Gauss-Jordan. The Gauss-Jordan elimination, you end up with this identity matrix for the coefficient matrix, and the solution vector is now the solution for your x and y. To get there, you follow the procedure of Gauss-Jordan. First, you create a 1. In this place, let me get the pen. You create a 1 here. Then you move down and you want to turn this 3 into a 0. Row 2 minus 3 times row 1. Store the result back in row 2. You get your 0 here. Alright, now I want a 1 over here. To get that 1, I just multiply by 2. So now I have my 1. Now go back up and eliminate the 0.5. You want to turn that into a 0. Right, so again, it's just a simple 2 by 2. Remember what the rules are. Any row, you can multiply a row by a number. Let's say a number is alpha. You can multiply any row by some number alpha. That means multiply the whole row by that number. Here I multiplied by a half. For the first, okay, I don't have the original matrix in front of me, but a half got me this. Obviously it was 2 and 1. All right. The second thing you can do is you can take rows and add or subtract them from each other, including multiplying by a scalar. So you can take row 1 and add to it 3 times row 2. That would be perfectly fine. Here's what you can't do. You cannot multiply by 0. You can't do that. The reason you can't do that is you'll wipe out your whole row. For example, say I want this 3 to be a 0. Well, if I take row 2 and multiply by 0, I'll get my 0 here, but I'll get a 0 every place else and just wipe out the whole row. So you can't multiply by 0. Knowing what to do next takes some practice. Basically, if you just want to change the value, for example, you want to change it to 1, and it was 2 before, or you want to change it to 1 and it's 0.5, you multiply by the number and let the rest of the row do what it wants. To create a 0, that's when you add or subtract the rows together. Now we compute the determinant. You can write the determinant and write the matrix after it, like 3, 2, 9, 6, which is what I did here. Also using what looks like absolute value signs around a matrix without any brackets, that also means take the determinant. And if you remember, taking the determinant means multiplying these numbers together, and then multiply these numbers together and subtract the green from the red. So here we multiplied 3 times 6 and subtracted from it 9 times 2, because that was in the other direction right here. Okay? The result happens to be 0. Now, the determinant has a very big meaning when it comes to inverses. If the determinant equals 0, there's no inverse. Otherwise, there is an inverse. Okay, so if the question says, does this matrix have an inverse, then you will take the determinant. If the determinant is 0, you'll say, no, it has no inverse. If the determinant is not 0, then it has an inverse. We only take determinants of square matrices. The square matrix has the same number of rows as columns. We also only find inverses of square matrices. On the next question, of course, is does the above matrix have an inverse? No, the determinant was 0, so there's no inverse. That's the answer for that. Now, why is this true? If we look at just a regular old 2x2 matrix, and this extrapolates to bigger matrices, then the inverse equals, you may not recall what to do. If A is A, B, C, D, for the inverse, you switch these two. Whoops, I need a pen. You switch these two around, so the D comes up here and the A is here. Leave the B and C alone, and you put negatives in front of them. There's other meanings for what this is, having to do with cofactor matrices, but that's all you need to know right now. The most important thing is, then it is divided by A times D minus B times C. Well, what is AD minus BC? That's just the determinant. Right? And here it's written in general. The inverse of the matrix is 1 over the determinant of A times the transpose of the cofactor matrix. Again, you don't have to know this last part here. Don't worry about that. The important thing that I'm trying to explain is that the inverse involves 1 over a fraction with the determinant of A in the denominator. If this is 0, then that fraction doesn't exist and there is no inverse. So again, the determinant is important because it appears in the denominator of a fraction that multiplies the inverse, or it's part of the inverse. So if it's 0, you've got a problem. Can it be negative? Yes. Negative is fine. Positive is fine as long as it's not 0. Now these kind of matrices are important in the digital age and all. So this is a connectivity matrix between 3 cities. So what we're talking about are communication channels, microwave links, right? Whatever. However, it's some communication channel between these 3 cities. In this case is Duluth, Biwabic, and Fargo, North Dakota. What this, the arrows mean is the arrow points from the source to, it's as though, okay, say you're sending letters. Maybe sending letters easier than microwave links. So if you send a letter from Biwabic to Duluth, this symbol right here shows that you have a path to send the letter from Biwabic to Duluth. Here you could send it from Duluth to Fargo. That's what that symbol means. Biwabic to Fargo. See that symbol? Alright, so from to. That's what the arrow means. Now the double-headed arrow means you could send it from Duluth to Biwabic. That's what this arrow head means. And from Biwabic to Duluth is this. So that means it's a two-way channel here. Again, there's another two-way channel here, and there isn't one between Biwabic and Fargo. Now to create a matrix out of this, we'll write the froms in this column and the twos in the as a column headings. The rows are from, the columns are to. So from Duluth to Duluth, there's no channel, so we just put a 0. From Duluth to Biwabic, well, Duluth to Biwabic, there's only one arrowhead pointing from Duluth to Biwabic, so that gets a 1. Okay, how about from Duluth to Fargo? Well, there was one here in a single arrowhead, and there's another one here, another channel here, so there's a total of 2. Now look at from Biwabic. From Biwabic to Duluth, there's 2. See, there's this channel here, that one-way channel, and the two-way channel, so there's 2. Biwabic to Biwabic, 0. From Biwabic to Fargo, there's 1. See that one arrow there? Okay. Fargo can talk to Duluth, and that channel, it can't talk to Biwabic, it cannot talk to Fargo. Okay, no Fargo to Fargo. So now we've created this matrix, we could just write it by itself. 0, 1, 2, 2, 0, 1, 1, 0, 0. Now we need to compute c squared and tell what is the meaning of c squared. C squared refers to forwarding. So if you send a message from Biwabic to Fargo and it's really destined for Duluth, and Fargo can pass it on, then that will mean that there is a channel between Fargo and between Biwabic, can go to Fargo and then go to Duluth. That's forwarding letters one time. And when Duluth gets it and says it really isn't for me, they say fine, it's just dead letter drop. They aren't going to keep forwarding it. I think the post office forwards through 2 changes of address. C squared is what you use to compute that forwarding. This is the connection matrix for forwarded messages. So here was our original matrix, and we square it by multiplying it by itself. Alright, I just for review, you take the first row, you go against the first column, and that creates your first term in this new matrix. Then you take that first column, the first row, and you go against the second column. That creates your second entry over here. So this first row creates this one, and this one by looking at the different columns. Then you move down, start with this row, and it gets multiplied against each column in the second matrix, and that creates this term, and this term. And here's the result: 401, 124, 012. This is the forwarded messages. And now you add them together. So here was this, let me get the highlighter. Here was the original connection matrix, and here is the connection matrix for messages that are forwarded once. So you add them together. Remember, in matrix addition, you add, let me find a highlighter. You add them cell by cell. The 0 plus the 4 gives me 4. 1 plus the 0 gives me the 1. The 2 here and the 1 give me the 3, etc. So you just go cell by cell, adding or subtracting the matrices. In this case, you want to add them. The reason you have more than one channel, you have that's called redundancy, is in case something goes out, you might still have channels left over so that the communication will continue. And this is a test of the system that we had before, and I'm going to try to write it here. You had Duluth, there was Fargo and Biwabik, and there was this, so there were, these channels were here, like this, and it was okay. Now the idea here is that something happens, some catastrophic event, and all these channels are wiped out. Can all of these cities still talk to each other? Right. So you go back and reconstruct the connection matrix for this case. So Duluth to Duluth, Biwabik to Biwabik, Fargo to Fargo. Those are all zeros right along the diagonal. Now, there was one channel from Duluth to Biwabik. It's this one right here. Okay, that's why there's a 1. All the channels between Duluth and Fargo are gone. That's why there's a 0 here. Right. Biwabik still has 2 channels to Duluth and 1 to Fargo. And Fargo has no channels to anyone from itself to anyone. C squared gives you this matrix. Adding them together, you can see that Duluth and Biwabik are connected with each other, and they can talk back and forth. Both Duluth and Biwabik can talk to Fargo. Fargo can't talk to anyone. In this problem, you're given information about 3 locations and their utilities: electricity, gas, and the rent. All right. You need to write the cost matrix. This is not specified for you. You do it any way you want. In this particular case, the rows were selected for the location. Location A, location B, location C, and here's your electricity, here's the gas, and here's the rent. It could have been written differently, with electricity on the first row, gas here, and rent here, and then the columns could be A, B, C. So however you do it is how you do it, but you're going to have to interpret the results later. Now you're given a matrix showing the change in costs. In this case, there's a 10% increase here, a doubling here, and a 20% increase here. And you're to multiply the cost matrix by this matrix to see what the new costs will be. So you can work out that multiplication. You find that 1.1 will actually multiply only the first row, the 2 only goes onto the second row, and the 1.2 only goes onto the third row. This is called pre-multiplying because you put the A first, A and then C, and you get one set of results. In this case, if you can look at this, remember this was location A in the first row. It means location A prices went up 10%, all of them. Location B prices doubled, right? And location C prices increased by 20% because the 1.2 only multiplied the third row and nothing else did. Also on the test, there will be something called post-multiply. Post-multiply. In that case, it's C times A. When you work out those results, you'll see that the 1.1 multiplies column A, the first column, the 2 multiplies the second column, and the 1.2 multiplies the third column. In this case, the electricity went up 10%, the gas doubled, and the rent went up 20%. So pre-multiply by A means put the A first, and you will get different results than if you multiply with the A second.